Okay, our next speaker is Alejandro Perdomo Ortiz from NASA, and he's going to tell us about model-based diagnosis in combinatorial, combinational digital circuits. Alejandro?
Okay, thank you. Well, it's a pleasure to be here, in particular representing this amazing team that has done this work. It's been already 2 years. Can't believe it. I mean, 12 people tag along in this very ambitious project, and I hope, you like it. So this work, from the NASA side, unfortunately, I don't have still the funding from my co-authors, but it's been largely funded by the QEO project. This was one of the first projects when we started playing with NASA. And yeah, so I think overall, we're not a small community anymore. I just had to introduce this morning two of my co-authors, so it's a large effort. So let me just put the work in context. So I think, if you've been throughout the whole conference, I think you've heard a lot of talks about benchmarking. And synthetic benchmarking are extremely valuable tool for just assessing the power of quantum annealing. So I think, for instance, we've seen, all the work from Google, from D-Wave, from, our NASA team as well. A lot of teams and the ISI, F4, the USC, all of those questions, they're tackling the physical aspects of quantum annealing. What is the role of noise, the importance of the uncertainty in the parameters, maybe new post-processing. So all of this is very valuable. But I think, all of these papers get a single bat. And that bat is, what about, what can you tell me from those benchmarking about a practical application? What is in there for extrapolating to a practical application? And I don't think you need to go and read Scott Adamson's blog to realize that this is an important question, that actually there is a need for really testing real-world applications. So that was the task that we faced. And actually, another question is, how close are really these instances from the real-world applications? And actually, the answer that we have in this paper that we're in preparation is actually they are quite different. Actually, they are quite different. So I think, anyone in this conference can relate to this question as well, or to this statement, and is that I think any single one of us here, we just really want to find out what is the most powerful computational strategy. Eddie Farr, he just gave a wonderful example of actually how can we tackle intractable real-world problems. So why is that actually we don't try that much? So simply because life is hard, and benchmarking real-world applications is harder than just doing random spin glass type of benchmarking. So as an example of that, you can see it since 2012. Since we have maybe the 128 D-Wave device, you see dozens of papers on benchmarking on synthetic data sets, but zero on a comprehensive study, and I will explain in the next slide what do I mean by comprehensive, on certain applications. So actually, the first mapping of a real-world application, actually that was during my PhD, it was in 2007, it's been 10 years. The first experiment on the first application, it was 2012, but and NASA and many of all the other startups that joined the effort, they've done a lot of work in application, but I would emphasize what do I mean by comprehensive and what do I mean by real data. Not just surrogate problems that resemble data. It's actually, let's tackle a real world application. So I will try to convince you in this talk that actually now merging these two perspectives, the physics perspective and the application perspective now is within reach. And that we should start adopting it, because I think the lessons that we learned is completely different from the insights that we are getting from the random spin glass benchmark. So now I think it's a good time to start doing this effort. So what do I mean by comprehensive? So what you will find in that paper that is in preparation is, definitely, of course, we focus in a real world application, and actually we tackle that application with 6 different algorithmic approaches, all the way from classical, like simulated annealing, state-of-the-art parallel tempering with isoenergetic cluster moves, that's Helmut. We have Quantum Monte Carlo, the collaboration with Google, and Sergei Isakov, who is here, has helped a lot. We have tailor-specific algorithmics for that application that comes from my industrial collaboration with Xerox PARC. Alex Feldman is there. He actually developed this one during his PhD, and this is a 2007 model tailored for this application, and actually that is pretty much beating all the classical algorithms. And we also had D-Wave experiments as well in this benchmark. And we also have this study in all the possible representations in such a way that we can study physics questions like, okay, so what is the role or what is the value of adding, let's say, or having a device with a different connectivity. Actually, here are the questions that we address in the study, and is from the application perspective, what is, for instance, what is actually the desirable features in a real-world application to maybe find a quantum advantage or a near-term quantum advantage? What is the payoff, for instance, of actually increasing the connectivity of your device? We've seen this a lot. What is the value of actually having quartic interactions, 3-body interactions? So we also tackle that question, or at least provide some insights directly from this benchmark study. And also, for instance, what happens if you change the annealing schedule? What is the impact of that? Or maybe if you add, is there any need for really more complex driver Hamiltonians, non-stochastic Hamiltonians? And finally, we also try to get some insights on, for instance, in quantum Monte Carlo, we know that it does not simulate the device or the dynamics of the device. But at least what can you tell about this computational scaling of quantum Monte Carlo versus D-Wave on a specific application, something that is missing as well. So that's basically pretty much, the work that is in preparation. And I will just try to, I don't have 2 hours to talk about all of this, but at least I will just give you a sense of 2 of these questions. And it's actually why, I will try to explain why benchmarking applications is hard, and also maybe one of the most interesting findings of this work. And you will see the paper hopefully soon. So let's actually just go to the application. And it's an application that, it goes back maybe to the 1980s when people were trying to diagnose digital circuits. And here I'm emphasizing only in combinational digital circuits. So what is a combinational digital circuit? It's a circuit that actually doesn't have any memory components. So actually, you give it the input, and you have the output completely specified by the input. So there are no actually, doesn't depend on the state of the circuit. So an example of that, you have it everywhere in your computer. It's just a multiplier circuit. And what you see here actually is just an example, a layout on a k by k multiplier. So basically, you take a binary digit with k binary numbers, and then a binary number with k digits, and then another binary number with k digits, and you just multiply them, and the product is coming out of this pipeline here of full adders and half adders, and at the end of the day, you end up with 2k digits that represent your product. So that's the standard thing, an example of that, and actually those are the ones that we use for the benchmarking here. And actually, so what we actually, to vary the size, as in any benchmarking study, in any asymptotic scaling analysis, we need to increase the size. So we go from, okay, let's multiply a digit that is 2 bits and another one with 2 bits and 3 bits, leading a 5-bit output, or we can take a 7 by 7 and giving you a 14 output. So these are the sizes actually that we can control. And what is the problem at hand? What is the combinatorial optimization problem here? It's not multiplication, it's not factoring, although we could do factoring here. Actually, it's a diagnosis problem. So you're giving the input, you're giving the output, you know the output is wrong. The question that you are asked is, tell me where are the faults in your circuit. Which gate is the one that is misbehaving? Is it 2? Is it 3? You don't know. So you just know the input, the output. Your task is to assess what is the most likable explanation of that circuit. So that's the application. And actually it has been used in benchmarking, and is constantly used as well in the electronic industry. There is a similar problem that is called the ATPG, automatic text pattern generation, that actually is related to this problem. So let me explain why benchmarking in real-world applications is hard. And a lot of, some of the talks here have highlighted this. When we are given the circuit, you're given the circuit in this language. It's a little bit boring, but it's just a bunch of instructions telling you, okay, this wire is actually giving you an AND gate between input 1 and input 2. So it's just a list of things that at the end of the day, you need to transform that to something that you can think of implementing in a quantum annealer. In this particular case, the first approach, actually we implement this into a polynomial expression that relates the binary variables. The binary variables here are the health variables for each one of the gates, because that's actually the answer. I want to diagnose for each gate, I need a variable that tells me whether it's faulty or not. And then you have some wires. All the outputs coming off this nasty circuit basically does that. So here, I have collected all these variables here in a representation P for polynomial and constrained binary optimization. A lot of people are related to this, and this is actually coming from one of the multiplier 2-3 circuits. And here are cartoons of the quartic, those are the squares, and the cubic interactions that you have in such hypergraph. So that's basically, if you can tackle the problem here if you had a device with those interactions. Now, of course, you need an efficient mapping. The second challenge is that you need to have an efficient reduction of the locality to a quadratic in case, for instance, you're limited to devices with pairwise limitations. And then you need to add some ancillance, to break those cubic and quartic terms here present in this graph. This is also actually a real graph coming from that application. Now, what is the next challenge? Is that the application needs to have a sparse graph in such a way that when you go to the quantum annealer, you don't waste all your qubits in the embedding. And at the same time, the application needs to be intrinsically hard in such a way that is interesting. So basically, I mean, this whole diagram basically summarizes into things. When you move from here to here, you're just increasing the number of spins, the number of resources. Here is a more compact representation. You go to the quadratic and you go to this one. And there is another challenge is that every single step that you take in this direction, you're changing the energy scale. Why? Because when you go from here to here, you add penalties, the reduction contraction penalties. And when you go to here, you need to set penalties to ensure that these qubits behave like as a chain, representing a logical qubit in this graph. So basically, the energy scale changes, and that makes things, and that's why it is not a minor thing when you go to the device. These problems tend to be with a small precision requirements. So you need to have a small precision requirements. They tend to be high precision requirements. So you end up with penalties of 1 million, and then some values of the order of 1. And then pretty much everything is washed out in the noise level. So that's one of the challenges. So that's what I mean by that. And just to give you an example of this application, a multiplier 4x4 has a representation of 64 gates in the propositional logic. When you go to the QUBO, you end up with 120 spins, then you go to 183. Then in the device, our experiments are of the order of 600 variables. And this is an overhead. So what is the challenge? You need to find an application that is hard at the level of the smaller instance. Why? Because the classical competition are going to work in these two. They're not going to work they don't need to go to chimera. They don't need to go even to the quadratic representation. That's the challenge. So basically, I mean, what you will find in that paper, we will try to make an argument why this application actually satisfies all these requirements. And that illustrates also the example. So let me actually, the first finding in this study is that actually these instances turned out to be harder than any other representative random spin glass instances that we see in the literature. What do you see here? So basically, the time to solution is just the computational effort to solve the instance. Here is the typical instance, the median value with the error bars. And then here is the problem size of each one of these instances. So if I just think of this data set as a synthetic data set to prove the D-wave. So all of these instances are in a chimera representation. So basically what you see is that, for instance, at the level of already 500 variables, these instances are already easily an order of magnitude harder. But the most important thing is that it's not only the hardness in that sense. The one that actually matters is the scaling hardness, the asymptotic scaling of these instances. And what you see clearly is that this application already, for all these lines that we're computing with the same algorithm, is parallel tempering plus ICM, self-consistent, fully optimized for every single instance of each one of the random spin glass and the application itself. You see actually clearly that the instances, when you calculate the exponent of this plot, that's the value of B here, actually it stands out that actually these instances are much harder than any of the other instances from a scaling perspective. It's not just a prefactor. So that's one of the main findings. As I said, these instances could be quite different from the other instances. And that's basically one of the first conclusions. There is a lot of things here in that study, and I'm going to have time to talk about the different we tackled the problem from an application scaling and from a physics scaling, but I'm going to focus on only one more thing, and it's the comparison of our simulations with Hamiltonians, including quartic and qubit interactions, and then the Hamiltonians, let's say, with pairwise interactions. This is what we refer here as quantum Monte Carlo P, with the polynomial, and then quantum Monte Carlo Q. And then simulated annealing, you can also run the classical solver on both. What was the striking thing that we found here? So anyone, I mean, I think have you seen in this conference, a lot of the experimental effort is going to building cubic and quartic interactions natively, just because you think actually it's a reasonable statement. There are many reasons why to do that. What we are finding here actually, and is good news, relatively good news for the quadratic expressions, is that actually notice the different behavior between quantum Monte Carlo compared to simulated annealing. Simulated annealing has an easier time in the PUO as expected compared to the quadratic representation. Quantum Monte Carlo actually has a harder time solving it in the native PUO interaction, the polynomial one, than in the pairwise, in the quartic than in the pairwise. This is completely unexpected, and I think our physics intuition of why this is happening is coming actually because since we still have a single transverse field, actually is not enough to traverse the very complex rugged landscape. And this is the first demonstration actually that just going and building quartic interaction is not enough. You really need more sophisticated Hamiltonians if you really want to take advantage of this compact notation. And here actually you see that the different behaviors. So here is simulated annealing, the result that I show you. The quantum Monte Carlo is reversed. The quantum Monte Carlo cubo is better than pubo. And then you see actually for parallel tempering doesn't make a difference, that much of a difference. And we also have an explanation of why that is the case. And how much time do I have, Elizabeth? Pretty much 15 already? Okay. So, I mean, this is one of the highlights of the paper, let's say. But as I said, I mean, I'm not going to even touch on this and the impact on the application. Just let me summarize here. So, as I mentioned, we have, this is actually the first study on an application that deals with comparison between classical and quantum algorithms and generation of these benchmarks. And here, I mean, I will just leave up this for conclusions. This is actually the real findings of all the studies. And as you can see, it goes all the way to limited quantum speedup. Just, I mean, I should say that actually we call this quantum certified limited quantum speedup. It's different from because, I mean, we didn't optimize the time and the D-wave, but I can go into details of why that's the case. And then basically, these are all the lessons that we learned for what would you expect when you're designing an architecture, the next generation of quantum annealer, which ones had the largest impact, and then also some of the comparison with the state-of-the-art algorithm. Okay, thank you.
Okay, we have time for 1 or 2 questions.
Questions? This one there, Andrew?
Did you experiment with any methods of modifying the transverse field on variables that were incident to the quartic terms? QMC?
No, actually, no, we didn't. So the only thing, I mean, and the only conclusion that we have from, for instance, for trying different schedules is we tried the usual linear schedule in quantum Monte Carlo versus the case of just the D-wave schedule on quantum Monte Carlo, and just to see just those 2 points actually was the impact of the schedule. And I think for the most part, our conclusion is that the schedule might change by the results. They enhance the probability by a prefactor, but we don't think at the moment from those 2 points they actually reflect. I think, I mean, the most interesting finding I would say is, as I said, is just actually the connectivity really plays a role in the scaling. And yeah, so the results related to the design of the quartic cubic versus quadratic.
Okay, thanks.
One more quick question. Ita?
So you said that you optimize the runtime per each instance.
Yes.
So I mean, if you do that you may not get what you would expect from the correct scaling, I guess, for random problems. Normally, what one does is optimizes the the runtime for a certain set of parameters, but not for any specific instance. And I think it's sort of a way to get sometimes the wrong scaling.
Well, I mean, I think it's the opposite. I think you might. I mean, it's a lot of more work actually if you do it directly on each one of the
That's
instances.
exactly what I'm saying.
Yeah.
I mean, it takes a long time, and you didn't take this time into account, right?
No.
But you could have optimized it to death. I mean, and if you optimize each instance for all the parameters, you get O of 1 time.
Yes. So I would say, let's say, if I want to include it as a prefactor, but if I want to characterize the intrinsic scaling of the algorithm itself, you should do it the other way. The only thing is that the other one is cheaper. So I would say in the other case, you might get the wrong scaling, but actually you will save time. But I think in the other case, you get the right scaling, but it will take you more time.
Okay, I'll try to
Yeah,
convince you
we can
otherwise
discuss
after.
Yeah.
Okay, let's thank Alejandro.